Okay, let me show you a method for finding the line of intersection of two planes. Now, this is a method I find quite intuitive and I think it's quite quick to do once you get the hang of it. So the knowledge or kind of the intuition that this method is kind of founded in is, if you, especially easy to see when you look at the planes graphically, is that this line of intersection between the two planes is just the normal to the two normals. I'll bring in the plane normals to make it easier to see. But if you just found the line perpendicular to both of the normals, that would give you the line of intersection. Now this information gives us kind of a way to go forward really. So I'm going to just extract the two direction vectors and we can just find the normal, or the normal direction vector, that is. Of course, we'll quickly get the normal using the cross product. And I'll just check what that is. That'll give you this vector, which of course you can just simplify to this. Now, if you think back to basics, we're trying to get a line here. And for a line, in vectors, you need two things, a point and a direction vector. So we need to find a way to find our point. Now, the way we're going to do this is by considering our Cartesian equations. Now, of course, the obvious issue here is we have two equations but three unknowns. And although this is an issue, it makes complete sense. If we were able to just solve, that would mean we would have a definite solution. But when you look at the planes, there is no one solution for that intersection. There is an infinite number of solutions because there are infinite points on this line of intersection. So what do we really do here? Well, we'll use a method that's quite similar to what we did when we were finding the perpendicular to two direction vectors without cross product, and that is we're gonna set z equal to 1. Now I'm gonna justify this. In 2D space, it's very easy to think if I have a line, I can give you any x value and the y value will exist. But when you take the jump to 3D, it can be kind of harder to understand why you can do that. And if you can do that, because there is some nuance here. Now, the fact is, here we could set x equal to 1, but we could not set y equal to 1. Now, the reason we can't do this is because the y component, I'm not sure if that's the right word, but the y part of the direction vector is 0. What does this mean? This means that there is one definitive y value. Y does not change. X may change, z will change, but y will never change. Y has a value. And if y was by some miracle 1, then y equals 1 would work. But it's very unlikely it will. You can't, like, you'll just be guessing the value. Might as well guess the whole point at that point, right? In this method, make sure you don't set, have a look, consider your direction vector, and set the value of one of the elements which is not 0. Of course, you always have one which is not 0, because if they were all 0, well, then you wouldn't have a line, right? You just have a point. So set the value. If, say, this was a 0, I'd say x equals 1. But for this example, I'll set z equal to 1. And just kind of, if you imagine just kind of a line, just kind of to try and convince you, if you're not already convinced, that in this case, for any z, an x will exist. Well, if I said z equals 0.1, well then lambda on this line, lambda would just equal 0.1 and then would be fixed. If z equals 56, well lambda would just equal 56. You can kind of see the lambda, since as long as you have elements here, the lambda can take an appropriate value to make sure that a point on the line exists such that it has z equals whatever you want or x equals whatever you want. But in this case, we cannot set a value to y because y has one singular value, and this lambda cannot change it since this component is 0, you can't times anything. You cannot times 0 by anything to get non-zero, right? Ignoring indeterminate forms, but that's a whole other thing. So I hope that kind of justified why you can say z equals 1. And now from here it becomes very trivial. We can rewrite these equations in terms of just x and y. I think that's right. I'm gonna just solve this. X equals 1, y equals 2. And of course, from before, z equals 1. And now this is our point of intersection. This is a point which lies on this line. And now it's just very simple. You just form your equation of a line, starting with your point, choosing any lambda you want, and then adding in your direction vector. Well, not any lambda you want, but any variable you want. Sorry, I misspoke.